All right, now we are going to calculate the pH at the equivalence point in the titration. And this is one of the most important calculations you need to understand how to do for titration. All right, so if you've watched the previous videos, we're still working with the same sample, 25 mils of a 0.5 molar weak acid solution, and it's titrated with 0.8 molar sodium hydroxide. And we want to know the pH at the equivalence point. So first we need to know what volume of base will get us to that equivalence point. So I use MAVA equals MBVB, where A stands for acid and B stands for base. And this is a 1-to-1 reaction, so it should work. So my molarity of acid is plugged in with my volume of acid, and then my molarity of base, and I solve for the volume of base, and I get 15.625 as my equivalence point. Don't confuse the word equivalence with the word equilibrium. This is the equivalence point. All right, so now we're going to set it up like a buffer calculation, and all of the HA is going to be reacted at the equivalence point because my moles of acid is equal to my moles of base at the equivalence point. So this is the fundamental concept of a titration. So I find my moles of my weak acid, which is 0.0125. And I have 0 moles of the conjugate. And I'm going to react the moles of strong base. So when I've added the strong base, it's going to be the exact same amount at the equivalence point. So I react all 0.0125 moles of the weak acid, and I make that same amount of conjugate base. So now at the equivalence point, I have 0 of the acid left, and I have 0.0125 of the conjugate base. So I cannot use the Henderson-Hasselbalch equation here. I do not have some of both. So I must do an equilibrium calculation. So I'm going to need an ice table. So I'm going to determine, and with an ice table you need concentration. So this is moles. I need to determine the concentration of the A-, and then I'm going to set up an ice table. And remember, for A-, you're going to need a KB. All right, so the total volume, because in order to find a concentration here, I'm going to need to divide by the volume. So my total volume is my equivalence point plus my original acid sample, gives me 40.625, and that's milliliters. All right, so if I take my moles and divide by the total volume, I get 0.3077. So that's what I have. And my KB is going to be 1 times 10 to the negative 14 divided by the Ka, which is 1.5 times 10 to the negative 6. And I get 6.67 times 10 to the negative 9. Now, both of these numbers are very long numbers in your calculator. Try to carry them through in your calculator. Another important note is that for this one, your calculator might show you 0.00000000. It might show you that value. And this is just a function of your calculator. If you convert it to scientific notation, you'll get this. So you cannot use this number with the 7 because it's greatly rounded. So make sure you're catching that. And always try to just carry the digits through in your calculator. All right, so I'm going to get a fresh screen. And I'm going to set up the ice table for the conjugate base. So now I'm producing hydroxide. All right, so the KB expression and my KB value, I'm going to set up my initial change in equilibrium. And I'm going to plug in the concentration that I calculated for my conjugate base. 0 of the product, and I'm going to move in the forward direction, so minus x plus x plus x. And then I get my equilibrium expressions. and I plug them in for KB. So I get x squared over 0.3077 minus x is equal to the KB of 6.67 times 10 to the negative 9. I'm going to use the approximation and end up with x squared over 0.3077 equals the KB. So I'm going to multiply both sides by 0.3077. I get x squared equals 2.051 times 10 to the negative 9. I take the square root of both sides, and I get x equals 4.529 times 10 to the negative 5. And you can check the approximation and find that it has worked. It's less than 5%. So my x, remember, is representing hydroxide concentration. So I can take the negative log of that to find the POH. So the POH is 4.34, and then subtract from 14, and I get the pH of 9.66. So pH at the equivalence point, when a weak acid is titrated with strong base, is slightly basic at the equivalence point, because you're producing a weak base during the course of the reaction. So if you're producing a weak base, it's going to be slightly basic when it gets done.